be applied over antennas where the power has to be calculated. So Friss transmission formula enables us to calculate the power radiated given that a known power is radiated. So in Friss transmission formula, we can find both power transmitted as well as power radiated with any one of the known components. And Friss assumes both antennas are isotropic, that means ideal in its characteristics, and that they are present in free space too. So we know that in the free space, there is no objections present to affect the propagation, and whenever we have to consider the free space laws, we have to assume all the environmental characteristics too. And in Friss transmission formula, we have to satisfy with the law of conservation of energy, because power radiated has to be equated to power received, and the energy leaving any closed surface around the radiator must be independent of distance from that of the radiator. So we won't consider the distance r from the radiator, and if it is the antenna, that is the transmitting antenna within a closed surface, we won't consider r, but the spherical surface we will consider. So because over the spherical surface only we are having theta component as well as pi component. So we are having in spherical coordinate system r, theta, pi. R is an independent variable, and theta and pi will only be considered to know the angular changes. Okay, so based on that only we are having amplitudes, that is radiation intensity within the over the antennas. So these things, this is the term what we have to consider while analyzing the Friss transmission formula. And with the free space laws, the spherical surface has an area of 4 pi r square over that region. The power and the power density will be uniform over that surface since radiation is isotropic. So we know the spherical surface area is 4 pi r square. So we have to consider that. And the power density, we know power density is P by the power over the full area. So the power density is given as S is equal to Pt by 4 pi r square, that is power transmitted by the area of the spherical surface where radiation is occurring. So Pt by 4 pi r square, the unit is for power it is watt and for area it is meter square, and so watts per meter square. But in practical cases, we are having non-isotropic source only. So for a non-isotropic source, the above equation can be modified by the antenna pattern to account for variation with the angle. And already I have told you in spherical coordinate system, the angles means both theta and pi will come over there. So with the Friss transmission formula, we have radiated power density as a function of radiated power and distance in the previous formula. So the maximum power that can be delivered to a matched load by a receiving antenna is given by P suffix r, that is power radiated, is given by power radiated is equal to the power density into effective aperture. For power density, we have already having the relation as radiated power by see here, S is transmitted power by 4 pi r square, and here it is radiated power. To get the radiated power, we are having power density as well as the effective aperture, and we know the effective aperture of the antenna is lambda square g by 4 pi, where e suffix e is to represent effective aperture, lambda is the wavelength, and g is the gain of the antenna. And for an isotropic antenna, the gain of the antenna is equal to 1. So the power received is taken as PR is equal to, gain is power radiated by power transmitted, so PR by PT, and to get the power received, PR is equal to PT into lambda square divided by 4 pi r the whole square. So just we are applying over this over here. So PR is equal to PT into lambda square divided by 4 pi r the whole square watts. And the Friss transmission formula assumes both transmitting and receiving antennas are isotropic, and so we are having this PRPT as what we have in the ideal case itself. Whenever we go for non-isotropic medium, we have to consider all the losses in the free space. So if we all the gain, power, everything has to be represented in decibels in antennas. So expressing Friss in decibels means PR is equal to PT C square divided by 4 pi r into f the whole square, because we are replacing lambda is by c by f as it is having the components from free space. So lambda is equal to c by f we have to consider, where c is the speed of the light, which is equal to 3 into 10 to the power 8 meter per second. We are writing it here in kilometer, and so 3 into 10 to the power 5 kilometer per second we have written. because here whenever we consider with antennas, it is for long range. We have to consider, whenever we are considering long range, the unit has to be kept in kilometers. So here we are taking all the terms in terms of kilometer. R is also represented in kilometer only. So we are having PT into 9 into 10 to the power 10 the whole square, as we have taken in kilometer, divided by the 4 pi the whole square, R in kilometer square, into F into 10 to the power 6 the whole square. So the ratio of power radiated to that of power transmitted is given as PR by PT is equal to 5.6993 into 10 to the power minus 4 divided by F in megahertz the square into R in kilometer the square. Taking log on both sides, we will get 10 log PR by PT is equal to 10 log 5.6993 into 10 to the power minus 4 minus. So the denominators will in logarithm will come in subtraction. So minus 20 log F suffix max minus 20 log R in kilometer. So the square term has been here. The square term has been multiplied with 20, with the 10 log. So power will, if it is a power term, means we can multiply it with the magnitude. So 20 has came here. So on substituting, on calculating the value, logarithmic value, we will get minus 32.44 minus 20 log F in megahertz minus 20 log R in kilometer, which is the free space gain in dB. So this is the ratio of power, the ratio of power radiated by power, sorry, received by power transmitter. And the effects of antenna gain are, over the free space channel model, signal from transmitter is having an antenna gain, free space gain, as well as receiver antenna gain, and received power in can also be calculated in dBm. So this is about a Friss transmission formula. And we will see one problem with the Friss transmission formula. A ground-based communication system transmits to a geosynchronous satellite located at 41935 km from the transmitter at a frequency of 1 GHz. The gain of the ground-based antenna is 25 dBi, and the satellite antenna has a gain of 15 dBi. Assuming free space propagation path loss, what must be the transmitted power in watts to produce 5 microwatt RMS at the output of the satellite antenna? Assume that the satellite antenna is matched to 50 ohm. So here the matching impedance is 50 ohm, and the transmitted power produces 5 microvolt, and the distance is 41935 kilometer. That's why in the derivation we have calculated with kilometer itself. The frequency is 1 gigahertz. The gain of ground based antenna, that is transmitting antenna, is 25 dBi. Satellite antenna gain is 15 dBi. So here we have to find transmitted power. Okay, so see, the power transmitted is V square by R, sorry, power received is V square by R. So we have substituted V value. Here V value is 5 microvolt. So 5 into 10 to the power minus 6 the whole square by resistance is 50 we know. So 5 into 10 to the power minus 13. So the power in dBm has to be written. So because we have to take all the calculations in dB only. So power in dBm is 10 log of the answer. So 10 log 5 into 10 to the power minus 13 and divided by 0.001, because we have to consider it in dBm range, dBm meter range. So minus 93 dBm. And substituting with the formula, which is PR by PT is equal to minus 32.44 minus 20 log of the value, which is 1 gigahertz, is, and minus 20 log of the, see, minus 20 log, here we are having kilometer. So kilometer is 41935 kilometer. So 41935, and calculating we are getting minus 185. So this is the answer we have to get. But we have to get, if the value is minus 93 dBm, what will be the power radiated, like that they have asked. So just calculate it from power radiated we have to find, right? So the ratio we have to put over here as minus 93 with the PR. Here we have to make change. and 25 minus 185 minus 15. So like this we have to write it in boxes, separate boxes, and we have to find what is the answer. So this is what the problem is.